All right, this is 610 number 3. It's a problem about a hammer and pulling a nail out of a board. Um, Something I've realized not a lot of kids have experience doing because, I don't know, that's just not a thing. Anyway, problem is you got a hammer, you got a nail. The nail's embedded in some wood here at some given angle that changes for everyone. And then there's a force from your hand, right? You're like pulling the hammer handle one direction horizontally in order to create some leverage to pull this nail up and out. So as you pull the handle this way, the claw of the hammer is going to pull the nail out of the wood. That's the main goal. So what are the forces acting on? We've got the force from the hand horizontal to the right. The nail is pulling down and left on the hammer. So because the hammer is pulling the nail up and right, the nail's getting pulled up and right. Third law tells us the nail then is going to pull down and left on the claw end of the hammer. You also have some forces at the point of contact. The question breaks it into like the force from the surface, X and Y components. I'm going to call that a normal force, vertically, Y component, and a static frictional force, X component. So that's what I'll solve for in terms of the force from the surface, because that's really what it is, and then you can combine them if you wanted the total force from the surface. The hammer also has a mass of 1 kilogram, so we should include its weight force acting in its center of mass. So game plan for all static equilibrium problems is add up the forces in all directions and the torques. So sum of forces is the force from the hand, positive direction to the right. Static friction is also to the right. That one's a little weird. Without the frictional force, if you think about it, if you pulled the hammer to the right, it would want to slip on the surface. So then static friction is going to hold that in and push to the right to hold it from slipping. Okay, hopefully that part makes sense. So that's why the frictional force is to the right, positive. If you were unsure, you could just put it in as positive and have the math tell you which direction it's acting in. But I think we can conceptualize that the hammer would rotate around its center of mass, and so to hold that point in place, we need a force to the right as well from friction. And then we also have a force from the nail, but we only want the horizontal component, so we have force from nail sine theta using the component, and then that's 0. Forces in the Y are the normal force up, positive, weight of the object down, negative, and then the nail is pulling downward on the claw of the hammer in the Y component direction, so cosine theta, force from nail. There. Set that equal to 0. Sum of torques. So always trying to pick the axis of rotation, even though it's not rotating yet, right? Got to imagine we're like, we're pushing, nothing's actually rotating. But we're going to pick the point of contact here between the hammer and the surface to be the axis of rotation, because that's where we'll end up eventually rotating. And that's where the two unknown forces are acting. So we want to pick that spot so we have the most unknowns at our axis of rotation. So our hand force is perpendicular to the handle, 30 centimeters away. No cross product needed there. They're already perpendicular. I'm going to go ahead and call that the positive direction for the torque. And then the force from the nail here, its vertical component paired with the 5 centimeters. So we got to actually do a cross product there just using the perpendicular component to the handle, which is force from nail cosine theta here times then the 5 centimeters from the axis of rotation. We're going to set that equal to 0. So there's our 3 equations and our unknowns. Algebraically then, you can get there pretty straightforward. I would start with my sum of torques, and that's pretty general for most static equilibrium problems, is you want to start with your sum of torques. That's usually where the least amount of unknowns are because of our clever choice of the axis of rotation, that we've got less unknowns there and we can get a first quantity out of that equation, and then we can work our way backwards. So we're going to use sum of torques to find the force from the nail first. Then we're going to come up to our Y equation. We're going to use the force from the nail to find the normal force. And then we're going to come up and use the force from the nail to find our static frictional force. And then, again, like I said, the static friction is your horizontal component of the surface force, and the normal force is the vertical component. Hopefully that helps.